My name is Tim Upton, and I'll be your host. First, I'll start by introducing our speaker, Rakesh Patel. Then he'll give his presentation, which will last about 20 minutes, followed by a 10-minute question and answer session. If you think of any questions during the presentation, please enter them into the chat box at any time. So now I'd like to introduce you to our speaker today, Rakesh Patel. Rakesh is the VP of Innovation at ADF Engineering and has over 20 years experience in engineering, project management, construction, and operations. His specialty is industrial water and wastewater treatment, and his experience spans across the food and beverage, pharmaceutical, chemical, biofuel, and manufacturing industries. Rakesh is a results-oriented, passionate leader who brings an ambitious focus to projects and strives to build long-lasting relationships while executing complex, profitable goals and fostering communication between stakeholders for successful project delivery. Rakesh holds several degrees and certifications, including an MS in Mechanical Engineering from the University of Dayton, a BE in Mechanical Engineering from Bhavnagar University, India. He holds a Certified Project Management certification from Xavier University and is OSHA 10 trained. In addition, Rakesh is a professional registered engineer in Ohio and Georgia. He's also a veteran speaker in the industry and has delivered several presentations at AOCS and the Project Management Institute of Southwest Ohio. So with that, I'll hand it over to Rakesh for today's presentation on taking control of your process water challenges.
Thank you, Tim. Good morning or good afternoon to everybody, depending on where you're joining from. So first off, I really appreciate if you would drop us an email to my personal email or through the link. If you would tell us what city and state you are joining from, what your role is, plant engineer, corporate engineer, executive, sustainability, EHS, whatever it may be, what your role is. And then if you had a specific interest, the reason why you joined this webinar, maybe you have an issue you're trying to tackle, or you just have a general interest in saving water or sustainability or whatever it may be. If you can find out what your interest is, we might be able to send you some stuff that is relevant to your own need later on after this webinar. So with that said, I'm going to get started. So here is the overall agenda for today's webinar. The goal is to discuss ways to handle process water challenges. And those challenges and opportunities are how to reduce your overall water usage and by correlation, the costs associated with water systems. We're going to talk about how water systems are closely interrelated to energy systems and chemical usage and things like that. I'm going to delve into approaches on how you go about tackling water challenges, how flow diagrams are useful, and benchmarking is very useful when you're looking to try to handle issues and make improvements to your water energy systems. I'm going to bring up some specific process improvements that could help out with reducing water uses, discuss a little bit on water treatment equipment and the associated improvements. And then next on, I'm going to touch base on how water and energy are tied together and how pinch analysis is useful in terms of both reducing your energy footprint and your water footprint and identifying streams that can be reused for beneficial use within your facility. And then next up, we'll look at some specific examples where you can reduce the water and also recycle and reuse water within your facility. So first up, almost everybody is aware, they've heard through news stories and otherwise they may have experienced it firsthand. There is scarcity of water in US. This is a recent chart from June of this year from National Center for Environmental Information. You see all this red and dark areas, purple, orange areas that shows about half of US, 45% of the US is under some kind of drought as of June of this year. And third of US is actually under severe drought according to this chart. So what does that mean for your facility? It may mean that you may have to have production slow down, or in worst case, shut down your facility because you just don't have enough water, or you're not allowed to draw water needed to operate your facility. You may have additional restriction on discharges, or it may be cost prohibitive getting fresh water or discharging wastewater. And that is impacting your production facility in somehow. And that's a business risk, right? Almost everybody has experienced higher cost of bringing in fresh water, and higher cost of treating the wastewater, and the cost related to the disposal, the volumetric disposal of your wastewater. It may also mean that you've gone over your permit limits somehow. And in best case scenario, it means wherever you're discharging the water, you're paying a lot of surcharge to do that because you're not meeting a permit limit. But in worst case, it may also mean that you've got notices of violation, and notice of violation can shut a facility down. So that's another business risk. Even if you are in a moderate area, and a lot of our clients have corporate sustainability goals, scarcity of water and increase in water related costs makes it that much more difficult to meet your sustainability goals. So what does it mean when you're looking at water and sewer costs? A lot of time people only talk about the water bill, which includes the charges if you're getting water from a municipal source and discharging it back to them to publicly owned treatment work. You get a water bill almost every month, every quarter, whatever your period may be, and you look at that. But water related costs are not just the water bill, right? There is energy cost in heating and cooling the water. A lot of water stream requires treatment. So there is chemical costs associated with treating the water. And if you're disposing it off, a lot of water off, then a lot of those chemicals are going down the drain. And then finally, you need labor to operate your water treatment equipment. If you have larger use of water, that is probably a higher labor cost, and then OpEx related to keeping up with the equipment and maintenance and replacing equipment and things like that. So wherever there is chemical or energy associated with water, those costs are several times order of magnitude higher than what just shows up on fresh water bill. So here's a quick graph that compares the increase in water cost between 2009 and 2019. So over the decade, fairly recent data. When you look at 2009 as the basis, it's the water sewer rates have almost gone up 60 to 65% when you take average. And in comparison, the consumer price index for all the other items have gone up roughly 20%. So water costs are almost growing at 3 times the rate of all the other items that are tracked in consumer price index, which is a huge number for a facility and a huge cost for the facility. So where do we start? If you want to look at your facility, the first place we recommend starting is doing some kind of water balance or benchmarking, right? Do you know what are the different flow rates for different streams of water that come in your facility or used in the process or in the facility in general, and what goes out? What is the specification in terms of the quality of that water is needed, whether you just need to remove hardness, whether it needs to be dim quality, whether it needs to have certain pH and certain dissolved solids and things like that. Do you have meters installed for different areas like chillers, scalder, wash cabinets, evaporators, condensers, and process users or not? The water usage may also vary, high, low, average, based on your production scheduling, based on the time of the year and seasons. Is that documented or not? It's been our experience that many of our clients can reduce thousands of dollars of water and sewer related cost by just evaluating their flow diagram. And then a lot of times it is a matter of finding leaks that you didn't know and fixing those leaks, but also optimizing the process and equipment, which we'll get into more detail here quickly. But this quick view is meant to show, what is your source water, whether it's municipal surface, well water, storm water, or you buying water in, what kind of treatment is needed. There's energy, electricity costs associated with that. How much water goes into process, cooling, utility, steam, housekeeping, domestic use, landscaping, others. And then are you currently reusing some of that water or energy back in the same process? That is what is shown in the green lines here, reuse within the process. You can take water from one process and use it in another process. That is shown in the pink/purple lines. And then after you've used the water and before it goes out, most likely you need to treat it. And it may go to a municipal source, what you call publicly owned treatment works, POTW, or it may go to an open stream, or you may have to pay somebody to haul it off. Some of our clients also have retention ponds for solar evaporation on site, or they may do some kind of on-site disposal, like spreading on fields and things like that. And then finally, this water balance diagram will also find water losses, like I mentioned before. There may be heat losses that you don't know about that will become apparent when you document your different streams. And then you will also know how much of your water actually ends up in the process, which for a beverage manufacturer, it's a huge component that goes out with the product. But even for food manufacturers, a decent portion of the water they bring in the facility goes out with the product in the form of moisture. And all that can be measured, it can be documented. So this is the overall water flow diagram for the entire facility. Once we do that, we can dig deeper into individual processes. So what you're trying to show here is you are making a product that needs to go from one temperature to another temperature as a part of the processing. For each and every stream, we can document the mass flow rate of the product that's shown in the pounds per hour. You can document what is the percentage dissolved solids. You can record the steam temperature, and finally the volumetric flow, right? Just measuring the flow is not enough to look at the whole picture when you're trying to look at water plus energy and trying to identify opportunities to reduce your use and recycle and capture a lot of the energy content before it becomes a waste stream. So in this process, first up, you're using steam for the final process heating. You take the condensate and use that condensate for reclaiming some of the energy in one of the heat reclaim system. And you return that condensate hopefully back to your boiler feed tank, right? You can take the residual heat that's available in your product, and that is shown in the black lines, your product reclaim heat exchanger before the product blows out and it needs to be cooled. You may use flash steam in your facility for preheating, and then you do your final heating with actual live steam. The condensate that comes out can also go through heat exchange. A lot of facilities bring in city water. And here what we are showing is you can recover wastewater stream on the right-hand side before it's discharged out. It may have some energy content that you can use to heat your city water. Then you can use condensate or live stream to further stream that water stream to send it to your direct contact. It may be fiber washing, germ washing is an example that you may be using water for that. And you heat that water to the required spec before the contact water becomes wastewater and goes to a wastewater treatment scheme. And then the condensate may go into that same wastewater stream, or it may be able to be recycled back to a boiler feed or put to some other use. This is just an example. This kind of scheme also helps you keep your wastewater treatment streams at a uniform temperature. That's especially important for biological system, so that you don't have variation in performance of that system throughout the year. And then whatever energy you are putting in, you may be able to recover a lot of that energy before discarding that water, for example, heating the city water stream. So this is a fairly detailed flow diagram that captures mass flow, volumetric flow, temperature, and the heat capacity of different streams, so that we can take this stream and then perform pinch analysis, which I'll get into here in a couple of minutes. But every plant should know different streams that go in and temperature for each stream. Just having a flow chart with volumetric flow may not be important to optimize the stream and do the evaluation. So process improvement, right? So by process improvement, I mean your manufacturing process or the core process that you do in your facility, your water quality requirements, the volumes that you're dealing with, your space and budgetary constraints. These are all considerations in order to identify opportunities for process improvement. First and the easiest one is look at the CIP that you use for cleaning your pipes, tanks, other process equipment. We see a lot of places, they use concurrent flow cleaning, meaning they're using fresh water for each and every step. And that water ultimately ends up as a wastewater stream. A lot of time the vessels you're cleaning are hot, and this wastewater also has energy content, which all goes down the drain. And sometimes it causes issues with underground drain, which may not be suitable to take hot streams and things like that. That problem can be easily rectified by doing a concurrent counterflow cleaning, meaning you're using your cleanest water stream for the finer cleaning, and then you are either flowing opposite to the way your product flows. So you're going from cleanest to the dirtiest, and then that stream becomes the waste stream that is discarded. And you can still recover energy, but the waste stream may go to a water treatment facility. Or you can also look at a multi-tank system instead of single tank system for doing your CIP. Other thing that can be looked at, improving the washing process itself. For example, spray balls are a lot more effective, need lot less water for tank cleaning compared to using something like a rotary impingement kind of cleaner, which were very common in facilities 10, 15, 20 years ago. But if you're not upgraded, then you may be using a lot more water than you need to for the CIP process, right? Next up, you can look at your heating and cooling loops, closed circle loops, and evaluate how much energy is needed to get to whatever specs you need to get your process, your product or your interim steps, and optimize this loop. A lot of places we see there's not very good control for the heating cooling process. And it could be as simple as replacing like a ball valve with a manual blow valve that can throttle the flow, or you can put in some automatic flow control and PLC-based control, depending on how complex your application is. That is how you're not doing, say, on-off controls, and you're optimizing your flow to get nearly uniform performance. You can upgrade your existing process equipment with newer design technology and use lesser water. Sometimes you can use enzymes or pH adjustments for, say, for degumming, and that uses a lot less water instead of just water degumming. Again, not every application is applicable to every plant. So you have to study the requirements and design a tailored solution. And that is what we bring to the table, knowing we are primarily process engineers, so we understand processes, manufacturing process. And then we can apply that knowledge to how to optimize the process and energy streams, right? So if you're drying products, starch, gluten, fiber, mechanically and then thermally, you could probably use some chemical dewatering additives in the dewatering step to reduce the thermal energy that's needed. If you're washing vegetables and using steam for peeling, maybe you can look at mechanical, flame, or caustic methods for peeling, and that will reduce your water consumption. You can also look at a lot of facilities don't return all the condensate back, and the condensate, obviously you need fresh water to make up for the condensate. You're dumping a lot of energy, so that's easy, low-hanging fruit. You can also collect and keep solid waste out of wastewater stream to reduce treatment costs and increase the reuse potential for that stream. So I have a couple more here, but there's a lot of different things that you can do to the process to reduce the water usage. or find ways to reuse some of that water stream, and then capture the keeping employees informed usually helps out. If people know where water is going and how much energy you are using, they are usually more mindful and come up with ideas that helps with reducing the water use. Next up, you can look at your water treatment equipment itself, find and fix losses. That's an easy one. Install low flow fixtures and flow nozzles so that you're not using more water than it's needed, and customize your application. Repair and maintain, especially older equipment. We see a lot of older equipment in neglect. Use optimal treatment based on your own and water quality demand. And an example I use here is a lot of times vendors have sold RO systems for low pressure boilers that we see. RO systems are great. They produce great water quality, but they're also energy hogs. You need a lot of energy to pump water through the membranes. You create about 20 to 25% waste stream that directly goes through the drain. And it just increases your water cost exponentially, whereas for just a low pressure boiler, softened water is typically more than enough to meet the water quality requirement without impacting the boiler performance. Put instrumentation, flow meters, analyze the data to see where water is going in, going out, and that helps identify opportunity to reduce. You can upgrade to newer cooling towers, for example, reduce lower the evaporative and drift loss. If you use ion exchange and you need dim quality water, CEDI is a great option that does not require resin regeneration using acid caustics, things like that. And then consider biological processes to reduce BODs and reduce the amount of sludge. I'm going to get into pinch a little bit quickly here. So what you're looking here is the red streams are the hot streams that require cooling. Cold streams are the cold stream that require blue streams are the cold stream that require heating. So what we can look at the temperature differential for each stream. We can look at the heat capacity. We can look at the available. So quickly here, the length of the bar is the temperature to and from that you need to get to. The width of the bar tells you the energy content that is available. When you feed this data into a pinch software, that identifies streams that are at identical temperature and has enough heat capacity available to do the heat exchange from one stream to another and recapture that heat before the stream moves on to the next step or it becomes a waste stream. We can match these streams up and extract as much energy as possible. And in the process, we can also reuse some of the water streams. So it's a combined analysis. So these are the quick step of doing energy water pinch analysis. You identify the streams, you document the thermal data, temperature, flow, specific heat. You feed this information into pinch analysis software and pair up the streams that need heating and cooling. And then identify energy recovery using heat exchangers. You obviously, everything is a capital cost. So you need to evaluate the feasibility by and the cost of pairing and optimizing, and then narrow down to stream that makes sense, both from technical and fiscal point of view. And then finally, once you've done that, you design the network of heat exchangers and piping to be able to capture this stream and reuse. So here are some of the examples of water reduction, like we talked, reduce your process water by optimizing manufacturing process, reduce water discharge from treatment process, softeners instead of ROs, optimize your CIP, reuse water from one system to another. You may be only using within the system, but there are a lot of time there's opportunities to reuse it to another system. Treat the wastewater stream to use into the facility before you discharge it. And then finally, a lot of industrial facilities may not be doing it, but a lot of municipalities are starting to do this, is you treat the stream and then you use it to recharge your underground or surface water sources, which later becomes a potable water use application. Here is a quick table of some of the specific applications. Like if you regenerate softeners on site, you can reclaim a portion of that regen and then use it later to fill up the brine tank, or even use it for low pressure boiler water feed. If you regen your dim vessels, you can use that portion of that reject stream for feeding high pressure boiler if you have it on site. If you soften your water before your ROs, you can take that RO reject and put it into cooling tower as cooling tower water feed, or you can send it to your scrubbers or other dust collection systems, dust control systems that use water. You can treat the processed water and then use it for floor wash downs or truck wash downs and things like that, utility feed, or even landscaping. And then condensate is a big one that results both in water savings and energy savings. You bring it back to your boiler feed and you recover the energy for heating processed water streams. So with that, I'll hand it back to Tim and we can take some questions.
All right, excellent. Thanks, Rakesh. So that was a wealth of information. So I'm sure you have some questions. We'll give it about a minute to let those questions come in. Go ahead and just type them in the chat, and then we'll let Rakesh go ahead and answer them. All right, so we've got a few coming in. So Rakesh, how does the presence of oils affect the ability to reuse water within a facility?
So it depends on the end use, right? Oils generally present issues if you're trying to reuse the stream for anything wash down or process water use. It will also present challenges in your heat exchangers because it will coat it up. But oil can be removed in several different ways. Simple step could be pH adjustment and gravity separation. If you have larger content or emulsions and things like that, you can use plate interceptors or dissolved air flotation clarifiers. We do this for a lot of our clients. And the water stream that comes out is more than 99% free of oil, and it can be reused a lot of different applications afterwards. So it depends on what you start with and where you need to end up in order to use that stream.
Okay, perfect. All right, we've got another one. So for heat recovery, what types of exchangers do you usually see most? Shell and tube, plate and frame, spiral?
So plate and frame, it depends on the cost component and the footprint component. Right, so plate and frames are subject to clogging, for example. So you wouldn't use that if you had a dirty stream with a lot of heat content, like a hot, dirty stream that you are going to discard, but you're trying to recover energy from it. You would probably use some kind of shell and tube, but it again depends on the solid content. Shell and tubes can also get fouling. And you may need to clean that stream up a little bit before you do the heat exchange. So that's one consideration. Another consideration is, say, if you're bringing in municipal water and you're wanting to heat it up with a waste stream, you're obviously concerned about if the heat exchanger fails and contaminants ending up in your city water that later goes to your process. So in that case, you can look at the pressure dynamics so that, say, your city water is almost always at a higher pressure, so that if there is a leak, it goes in a different direction. We can look at dual heat exchanger, where you are using a closed loop to do the heating for the city water, and you're using the dirty stream to heat that closed loop system. So there are several different considerations. That's a good question. You need to think about what your application is and put the right kind of, use the right kind of heat exchanger, both from a technical application point of view, cost point of view, and the space and the distance that you are dealing with for the streams that you're putting through the heat exchanger.
Okay, and we got time for about one more question. So is it cost effective to install a biological system for BOD reduction?
So to that, I would say yes, in the sense that biological systems have come a long way. Even in only last 10, 15 years, traditional biological system used to be an open tank or a municipal kind of system, which is equipment intensive, labor intensive to operate. But newer technologies employ membranes for cleaning up the treated water after a biological system. So the water that comes out is fairly clean and a good candidate for reusing. The overall footprint and the costs for these systems have come down too. So MBR is a good technology. It's called membrane biological reactor, and even MBBR, moving bed biological reactor. So small footprint. You have floating media on which the bugs grow, and give you a very effective system in a very footprint at a very attractive cost too. A while ago, if you wanted to put an anaerobic system that produces less sludge and also gives you some methane for energy, those used to be only applicable for larger volume, high BOD system. But recently, there are a lot of manufacturers who come out with what you call micro scale BODs, where you can apply that to small volumetric flow, and even, without excessive BOD loading, you can produce energy, and you can clean up the stream and apply biological system if you have BOD/organics as a concern in your wastewater stream.
Okay, thank you. All right, so we got one quick announcement for you before we wrap up today. So our next webinar is going to be hosted by Nathan Deutsch. It's going to be a complement to this one today. It's going to be about energy pinch analysis. So Nathan's going to do an in-depth review of pinch analysis software and the capabilities and how that may apply to your facility. So we'll be sending out more information on the exact date of that once we get that on the calendar. And with that, we just want to say thank you for attending this webinar today, and we hope you enjoy the information. If you have any other questions that you think of, you can always email Rakesh at rpatel, P-A-T-E-L, @adfengineering.com. Thank you.
All right. Thank you, everyone.